All right, folks, we're ready to start our last talk, which is going to be by Maani Ghaffari, who is an assistant professor at the University of Michigan. And he occupies the interesting position of maybe being the link between the filtering equivariance folks and the learning equivariance folks. He's going to talk about some cool stuff. Briefly, before Maani starts, I want to plug everyone to vote for your audience favorite poster at this link. Voting will close at the end of Maani's talk, so get your votes in real quick. Vote for 3, and it's not ranked, there's just 3 you really liked. And with that, I'll hand it over to Maani to tell us about equivariant theory and artificial intelligence.
Thank you, Jake, for the introduction, and it's an honor to be here. This is a wonderful workshop, and a lot of amazing people are here, and we heard a lot of great talks. So some of the examples might be related to papers that my students submitted. I think those should be automatically disqualified from the award if my name is on it.
You weren't part of the committee, so you don't have any say.
Oh, I wasn't. Oh, great. So, and I just want to acknowledge that we had a workshop in CVPR, and I'm going to reuse some of these slides. I put Justin and Cynthia, but Evangelist from Costa's group prepared the original slides from last year. And with that, we heard a lot about symmetries today, and a physical perspective that I think maybe is less discussed is that the laws of physics should be invariant to the observer frames. And that's also, I think, obviously Rob's work on control touched on it because there was actually dynamics and Poisson structure. And that invariance is also a good principle, I think, on finding out among all the mathematical structure, what is it that actually will work in real world? Probably something that respects the physical laws. That's a sort of good beacon maybe to follow. But on the mathematical structure of it, we've seen this a lot today. My goal is to obviously give it a more learning flavor and draw connections when I can, when I know. And this will be on the machine learning side and vision. Equivariance, obviously, we have the commutative diagram that the action of some symmetry group on the input will commute with a map. And that map could be, for example, the analytical lift that we saw in the equivariant filter, or can be a neural network. So if it's invariant, the feature field will not change as the input, for example, rotates. And if it's equivariant, it will transform in a predictable way with that rotation. And it has it's not new. It has an old basically history from mechanics to vision. These handcrafted features, obviously, they were invariant to some extent to whatever scale and other things. And the original convolutional network that was translation equivariant. So, but to give you a non-exhaustive list of equivariant neural networks in the literature, you might be familiar with this, or you might not be, but sort of this could be a good primer if you want to start diving into it. You can start reading papers on these topics. The first approach was, or is a regular group convolution. And that's a very straightforward way of generalizing traditional convolution to group convolution and obtaining equivariance with respect to a group. A more perhaps sophisticated version of it that is more scalable is a steerable network. And that's that gets involved in the sense that now we need to talk about representation of the group, something that didn't come up a lot. In the previous, perhaps, the work, we talked about Lie algebra and some specific vector spaces and group representations like adjoint. But here we're talking about irreducible representation and something that you can think of it as a generalization of Fourier transform and having certain bases and frequencies. Another class is equivariant MLP. We can have MLP and then make that multi-layer perceptron equivariant to certain transformation. These are also very interesting, but not as scalable as convolution because they don't have weight sharing. And there are 2 other categories that probably there won't be any time to talk about them. There are some slides, but I don't think probably we'll have time. But these are, I think, are very important. And graph, for example, is very important in modeling dynamical system and physical system in discrete form, but also a lot of problems are naturally on graph. So it's a good unifying framework, and transformers obviously are the state of the art for computing a lot of solving a lot of problems. So I want to draw some similarities between perhaps something you heard in linear systems course on convolution to connect it to the systems theory that we learned today. So convolutional neural network, there's a function or signal f of x is coming in, and then there's a kernel in the sense of 2D grid. It goes over it and computes the convolve basically the signal and gives you the output based on certain operation. If it's in discrete time, which is often the case when we implement, it has a rule and you can compute it, and that's it. You get the output by integration. Now the nice thing is that if you again compute the features before or after transformation, you get the same result. Now you might remember linear systems. This is a state space model. And you might also remember that the solution of this system was convolution. So it's not, I mean, people know that, but it's not really something that they're actively trying to work on it in the sense of group version of the convolution. But in any case, for linear system, convolution is the solution. So we could expect in principle that running a layer of convolutional network to be nothing but just computing convolution, but now we're optimizing the weights to find out what's the output. So that's, in that sense, it's not so much of a black box. It's just a different way of implementing your model, and now you leverage optimization to optimize and tune the weight. And of course, you get discretized, and then you get the time difference equation. And for example, if you do the Euler, that would be something that you see as a skip connection and ResNet, right? So we have the ResNet layer and then this Euler style integration when the input signal stays, and then there's a delta term that we learn. And that sort of is very similar to ResNet, which was then later generalized to a continuous depth binaural ODE, which will come up in one of the examples. Now, the group convolution is pretty straightforward. It could be overwhelming if somebody doesn't have the background, but if somebody's sort of comfortable with the structure of group construct, algebraic concept of the group, and obviously, if the input is on some form of groups, then we need to operate based on group action. So instead of taking the difference, we just perform the group action, and we integrate now over the group instead of Euclidean space. But that's obviously easier to say, right, than actually implementing it, because for something like a bigger group that will come up, you might have 8 or 9 dimensions, right? A library like PyTorch doesn't even support this level of, complexity. You can have maybe 3D or 4D, and you need to implement it yourself, basically.
I mean, you lost your signal, right? The signal is X tilde, and now you've made the signal an G tilde, right? So you
Yes.
the signal space. Right?
Excellent question. So the input signal originally is not on the group. So what happens, the first layer of convolutional group convolution network is called the lifting layer. The first layer takes a convolution, lifts it from the input, basically domain, to the group. Then after that, all the layers will do just regular group convolution. That, right. And that lift, I know there was a very interesting conversation about the lift. This is another lift, right? That comes up, and it is literally the same idea. Your data is on some manifold, typically machine learning, Euclidean space. You need to lift it, and it's lifted by convolution. which after that life is easy because then everything is on the group, right? But it's absolutely true, right? Because this is f of g, this is a function of the group. But in the beginning, the image obviously is over a grid. So the simplest case would be that you would want to integrate over maybe one additional dimension, and that would be SO2 rotation, right? We have the 2D translation, and now we want to have 2D rotation. Then the features that we learn, for example, if they're invariant, they would be agnostic to the orientation of the image, which is pretty useful for image classification. There are a lot of arguments whether humans are equivariant or not. Apparently, we're not. If you make the picture upside down, it's not very easy for us to detect. But it's to a good degree we are if you move it. It's biological systems might not be perfectly equivariant, but I don't know about you. I take some inspiration, but not a lot from biological. I mean, Kostas can disagree on the panel, and he knows more on neuroscience side of the learning. I find the math part more inspiring, to be honest. Okay, so how do you do it? You can't just compute that integral as a big S. We're going to turn it into a sigma and discretize it. When you talk about circle, it's obviously very easy. You are discretizing the interval between 0 and 360, and maybe you pick every 10 degrees or every 20, every 15 or every 30, and that's fine, it will work. But when you go to 3D, you get a lot more options. And some of them will sort of abstract the group into a really simple shape. Or some of them, like icosahedron, is sort of a little more involved. Some of them are symmetric, some of them are not. You can obviously do random sampling. You could do Monte Carlo, for example. But if you do it geometrically, like basically Euclidean shape, you don't need to rely on random sampling.
Okay, I'm going to ask questions, right? So this is a sampling, it's a sphere, right?
Yes.
Which is not a group. So
If well, we could do it for SO. So the circle is easy. We discretize the circle. Now we want to discretize SO3.
yeah.
We get to the sphere, but initially it is SO3. We want to discretize the whole in 3 dimensions.
Just looking at discretizations of the sphere get you there.
So we have, I think we get 60 configuration, or anyway here. So you get, I think here is good. So we get, you can go by, vertices or faces. Say each vertex is a configuration orientation.
Well, no, each vertex is a direction. So then you've got a whole SO2.
And then we have another one. We get five more, right?
Yeah, you get your.
So we can imagine the sphere, and then another, say, roll.
Right.
That has 5 more.
Yeah, but I mean that's not even a parallelizable system, is it?
Not really.
I think if you take, if you take S2 and you put a fiber off it, that's not SO3, right?
This is pretty much the over.
Yeah, I mean it's okay. Yeah, I mean so you've got some sort of sampling, but it's not uniform or anything.
No.
Yeah, think simply. Think that's the representation. The final. This is just it's like 60 representation, and this is the
That's a good way, I think.
like a finite representation. You can think about it without shapes. That's the representation.
Yeah.
But if you get the cosine, it is satisfied by the representation.
Thanks, Kostas. So I guess that's why we're here. This the way we think about the problems, I think, differently. It's also important. So we are after a finite, basically, set of group elements to just run the summation, basically.
Yeah, it's on the sample
There's-
of FO3
That's
as even.
That's, and we can do it very coarsely, or we can do it finely. Obviously, that will make it more and more expensive if you do it finely. So this is I think that was the sort of the first version, which is not very elegant. It's a very brute force way of doing convolution. And then one problem that's in the paper that I think Rob you mentioned as well, Taco and Max Willing published. And there are other works in this area that if you just do convolution over the shape, then the features in these two faces probably are similar, but then you want to pay attention to local, more detailed features. Some areas are more important. So there are other works. There are many, work around this work, obviously. It's a well-cited paper, but this attentive group, equivariant convolution, considers this local, you want to say, importance of the feature. Okay, and convolution, obviously, we can do it for finite groups as well. That's already a discrete sum. Now, if we want to do it for, say, at E3, that gets a little more complicated because if you can correct me, Rob, if I'm deviating from the new way of thinking about it, but think about SE3 as coordinates frame, and we have bunch of points in a point cloud, and we want to run this through convolution. So for every coordinates frame that I have for its position, I need to consider all possible 3D orientation.
Your coordinate frame has 3D orientation. So you're saying fix a point in space, and then allow all of the rotation of that point in space.
So that's what needs to happen in the group convolution. So I consider full 6 degrees of freedom.
And then what do you move the point around as well?
Well, yeah. So the typical Euclidean convolution will handle the translation part as usual.
Okay. But that'll be a direct product structure. That won't be an SE3 structure. You treat the two separately.
But for every point, we handle, say, if for every point, every translation convolution that we run, we consider all possible orientation. Then,
But you still, what you should be getting is as you. Yeah, okay. I'll think about it. Obviously, I've kind of worked in this area. Just trying to understand.
they do separate in practice. So
Which is a direct product.
Yeah, so-
in sense, you're just treating you're just treating it as SO3 plus.
right. And that's already hard enough. So it will blow up basically. So, and there was a work called EPN, and that's what basically they did. They directly go ahead and run the convolution. They do some simplification along the way. It's not, the full convolution that you see right down in the beginning. And then, so Minkan, this was the work that I was also involved. There's something more interesting that maybe is more related to this equivariant system theory, that you don't have to run the convolution over the full group. What we can do, instead of integrating over the group, we can go to the quotient space. Now for SO3 is very understandable. The quotient space, if you pick basically SO2, basically instead of 3 axes, if you get rid of the z-axis by quotienting G with this subgroup, what is left is 2 sphere. And 2 sphere, by this process is the homogeneous space that SO3 is the symmetry group. And the way, you can imagine it is that you have the sphere is completely homogeneous. If you close your eyes, no matter how I rotate it with SO3 rotation, if you open your eyes, you wouldn't know. Nothing has changed, right? So it's a symmetry group of that sphere. And what is interesting is that we can derive a relationship between kernel of this convolution in the quotient space and the kernel of the convolution in the original space. And then we can integrate over a lower dimensional space, in this case, 2 instead of 3. Which is...
Can I ask a question on this? So when you do this, right, in your neural network, you've got collections of, no, your neural network has, these are the convolution filters that you're running through it, right? So these then are S2 objects that you're putting into the convolution filter.
Right.
And then running across the nodes. Right, because but the nodes have to be S2 as well, right? Because that's what you're actually doing.
No,
So because you're doing a convolution on S2.
So in the group convolution neural network, the nodes, the activations are the same as old ReLU nonlinearity. There's no need to, because they're element wise, so it doesn't change anything about the feature. Like that's
Only enough. It's only when scale the outputs are scalars, the bunch of scalars.
Yeah.
Then it's pointwise. If the output is a vector, it has to be something more possible.
Yeah.
that's the the steerable version that we get into.
You have more like vector neuron. I think the kernel, which is 6 times the identity element of the subnet.
I'm confused because you're in a layer of the neural network, so you have a signal that's sort of in the nodes, right? And then you convolve onto that signal. You're doing that through this group structure, right? So it doesn't have to be. I thought that was what you said when you said the lift, right? So the first thing you do is you lift the information into a representation that you can think of as group elements. Yeah, and then when you convolve, you're convolving with group elements, right?
Well, it has group elements, but you can think about this feature map as some tensor that there is a dimension that say this D1 is the group dimension, discretized group dimension.
Yeah, so each.
But then there is another one that these are the outputs of the convolution. These are features that comes out of the convolution. So it's not, and this can be a matrix itself, and so it's not. So it's not that we're tracking one element in group convolution. We need to maintain that discretized group dimension as a geometric dimension. And then there are channels. These channels are features that comes out of the convolution filter.
Yeah.
That's so that I think the quotient space, I find it intimately related to the framework of filtering. And the idea is that if you integrate the quotient space, you drop some dimensions. That's but no, in general, in the learning framework, the difficulty is that people need to compute the constraints on the kernel. But what we've seen in today, I think, is not a challenge for system theory people. But that needs to be done analytically in this framework.
Maani, you say that the kernel is defined on the homogeneous space, but then you write K of C. Has to be K of C times the stabilizer times the.
Oh yeah. This one is not. This is not correct. This is not correct. Stole Minkan's slides.
Correct.
I'm gonna pin it on Minkan very soon. Not here.
G should be replaced by the variable on the
in
base, right?
in the sphere.
It's on the sphere.
It needs to be on this right. So the input of the kernel.
Is the
And it's
projection from the group to the.
So it's actually phi of G acting on some Z reference.
Right.
Kappa of phi of G acting on some Z reference. And
They're
then
not-
F of G acting on X. And it's integrated over G, right? Because that's the G variable. Yeah.
It's integrated over the sphere.
It's not, it's okay. So
The integration is yeah.
The measure.
So we
of the sphere.
measures on the sphere.
right. We need to change this in the measure, right?
Okay, and G times X applied on the stair, but then the G doesn't vary.
I think this is something like a correlation problem. Okay.
Let's not get into it. Yeah, every paper they write, they say convolution, but they write cross correlation. This is the
Right.
yeah, it's because that's apparently easier to implement. It doesn't matter. If it doesn't matter, then why they write it?
Yeah, I think for you guys it matters for Python.
But at least they fixed the deconvolution to convolution transpose. That was very confusing. Okay, so I think this was a beautiful idea and made it, instead of 60 elements, for example, now we're integrating over 12. And what is interesting about this particular case is that because when we go to a quotient space, we lose a degree of freedom. There's no reason we have to get it back. But in this particular case, if I don't know if you go to higher dimension, we can do the same trick. But if you paint every vertex of the icosahedron by a unique color, give it a unique ID, then every possible discrete rotation is just a permutation of this shape. So in principle, we could have we try as a supervised layer, and then you can recover the full 3D transformation. Because you know all the possibilities that you can hard code it and then supervise a layer to tell you to classify which one from 1 to 60 you are in. Once you know your configuration, then you know your rotation up to discretization. So that's good. It's possible to recover the full transformation. So what happened, I think this might be interesting, that in terms of memory, it's much more efficient. In terms of the speed, it's also much more efficient doing this quotient space convolution. So that the difference was, so one dimension difference was a lot. So it made a big difference. And this is not, a network that you ran through TensorRT or optimized. It's just, some lab model and that stuff. So you could, this potentially could be real time, this E2PN work. I think you could do real time point cloud processing. And for example, what Cynthia did for this, you have a point cloud and then you build a place recognition network in robotics, which you learn your features and you do max pooling. That will give you invariant features in the convolution setup. And then you can aggregate them to build a global descriptor. And these global descriptors are something that you want to identify places that later you revisit based on this point cloud problem. This is called place recognition in robotics and vision. And it's really cool that when we train this network, you grab the same point cloud and then apply translation and rotation, all 6 degrees of freedom, and the features that we get are very robust and invariant. A little jittering, but it's very easy to train a classifier on this feature to detect it's the same place. This is an ideal case, right? The full same point cloud. In practice, you're gonna have noise, occlusion.
So is the wiggling can be attributed to the fact that it's the discrete approximation of the group, or
could be that, could be numerical error. I think single, the friendly define, better. Is it single precision aspects of processing data, right? Could be a lot of, but it's nothing that will affect your classification results, right? So when you classify in an ideal case, it's really boring. You get 100% accuracy. It's not the case in practice. I'm just, this is a conceptual case that I think is really cool, that you can grab a problem and then in a sort of lab setting, you can solve it 100%. So I think this shows the power of equivariance and just leveraging this geometric information into the model.
I guess the question would be, so that sounds exciting, but since I'm not in machine learning, is it just that if you didn't use equivariance, you would get 100% in the lab?
Let me see if I have the slide. You don't. The
Just,
features are all over the place. Cynthia has that slide, my former student. I always ask for it, and I never got it. She has a slide that they're side by side.
Right, okay,
They're gonna take my words for it, but they're all over the place.
okay.
It's very unreliable because
People do this anyway, right, without your experience.
they do it and
It's place recognition.
it's not going to be 100%. It's going to be
Even in the lab.
something like this. Sometimes it's good. If you go to, so in large transformation regimes, usually the performance drop is significant.
Yeah. Okay.
Small,
So
you get away with it.
Locally, it does a
It's-
pretty good job if you go far away.
Right. So a lot of selling point is on large transformation.
So, I mean, I can probably just pre-process the point clouds, like I can choose some kind of covariance matrix to it, figure out the eigenvectors.
You take the mean and the.
Just align the data so that it knows it's the same to the network and then I don't get you.
Yeah, that's a whole branch of equivariance called canonicalization.
And this is basically like SIFT, right? Like they get the rotational invariance, they work out the.
That's the equivariant by canonicalization.
But isn't that much cheaper? Because now I just have to I don't have to do this integration of the high-dimensional space.
You're over 3D, right? We could use covariances.
It depends how you, whether you can do the canonicalization. The PCA is not.
PCA won't be robust, right?
PCA has all the symmetry. Or symmetrical or reflecting.
Yes, yeah.
But it is a line of work. I think that's one powerful idea is like causes canonicalization too. Then once that's done, then it's a local problem, right?
All this becomes.
Yeah. Which I always think, yeah. So I can finally say this. Whenever I say this, people look at me and they think there's something weird. But I find canonicalization akin to driving the aerodynamics or formulating an error state filter, because now you're localizing it around the identity.
Yeah.
So I find these two ideas very similar, but they're very far. One is a dynamical system, the other one is in just this data doesn't have time series, right? It's just one time step. And like if you drive this kitty sequence A, the driving scene, you drive from the opposite side of the road, it's not trained on this data set. You know, if it's not equivariant, you get 3%. It's what's the metric? I think it's accuracy. You get 3%, and then otherwise with 60% still is maintaining performance. So it's all about large transformation, which happens in place recognition. So I think these are very cool ideas and powerful ideas for extending very old convolutional networks to the equivariant setting, and they're pretty straightforward once you get a hang of it. But they're very limited to the small groups. They're really not scalable. And for example, if you have SL3, that's the set of transformation that acts on 3D, say, points, objects, and preserves volume. You can stretch, and you can have shear, but to preserve volume. Or in computer vision, there's homography or change of perspective for planar objects. So if this group is 8-dimensional, if we discretize it, very coarsely, and then if we have 40 by 40 image, like MNIST, and then if you pick just 128 features, we already need some 13 gigabytes of memory. So after 1 or 2 layers, you're out of memory. So there's no way to build networks for larger groups like this by this method.
Could you just explain the 5 to the power 6 for me? So you've got an 8-dimensional group, and so the discretization is going to be 5 to the power 6.
I actually don't know.
Yeah, it goes.
But
5,
so
5, 6.
SL3, we have SO3, that's the 3-dimension, and then we have one diagonal. If we do the CAN decomposition, we have SO3, and then we have a diagonal.
Normal.
Right. We have
It's like 2, and then the scale, and you throw the scale out.
We have.
I mean, if it's homography, you can get away with
Well,
every 3 a normal direction and a scale.
The scale is like AB 1 over AB. It is to preserve volume. It is 2 degrees of freedom, and then we have shear, which is you keep 1 on diagonal, and then you have X, Y, Z. 3, 2, 3. Makes it
It's
8.
40 and 40. So there's.
Yeah. No, there's no translation. 40 by 40 is the image size.
But that's not good.
So, but if you know this 8 dimension, even if we pick 5 points for each, it's not this number. It's already it's gonna be 5 to the power of 8, right? But yeah, I need to check. That's 6.
There's only one way to do the convolution. If you create the copies of the mother, you can do it also for yellow. Like harmonic networks, and then compare.
So the Fourier domain, do you consider the Fourier version and the steerable sort of in the same category, or you think they're different?
Yeah, well, we usually okay.
Because I didn't include the. I know.
Both the steerable.
I think next year Ying Xuan should give a talk. That's not my job. That's too hard. A very interesting work on the Ying Xuan and processes on the Fourier-based sort of version that there's some vector fields. The outputs are vectors, and then we can use Fourier transform to
No, before,
learn them. Not that.
Going into vectors, get very basic signal processing. You can save time by doing the operation either the space harmonic or depending on the
Right. The previous one is just brute force, but it's still it won't be super scalable, right? So maybe for that's so the steerable convolution is interesting because it uses the old idea of basically transforming the kernel, putting a constraint on the kernel instead of integrating over the group. And this is by realizing that if we have a bank of filters and say this one is at 0 and the other one is at 90, if you need the filter at a particular rotation, this can be obtained by a linear combination of these two bases at 0 and 90. So to have this is for 2D example, but for group, so if you have this basically kernels or bases on the group, a linear combination of that could give you different transformation on the group. And what will happen is that instead of computing, integrating over the group, we can integrate over the original domain of the signal, but we can put the constraint on the kernel to be steerable, meaning it changes based on the group transformation. There's a little bit of math to drive this condition for this intertwiner that sort of imposes steerability. But then after that, it has no problem processing images or big images because it's as if you're just running a regular convolution for processing images. It's just that this becomes much harder, and we need to rely on a concept that I would say is totally unknown to the engineering curriculum: irreducible representations. So if you're a physicist, we have one here. They did the inflecting work. So probably learn it in undergrad, at least for spheres and the spherical harmonics. But this never comes up if you're getting an engineering degree. Right? So okay, so these are, you can think of it as different sort of frequencies, so different bases, and then you can compute a linear combination of that and perform convolution, right? For compact groups, for example, if you pick a finite dimensional vector space, or if you pick a vector space, you can have a finite dimensional representation using these EREPs. But if the group is not compact, then that's also infinite dimensional, which is a problem. Also, if the group becomes higher dimensional, non-compact, not necessarily all of them are worked out, and you can grab a book and just use them. But for SO3, I think it's pretty standard. You can, and that you see that a lot in the literature.
Are you doing just a real convolution over here, or like a distant convolution, because you have an imaginary?
I think they do real. They don't do complex, right?
Cannot be real. Cannot be real. You have to do it with the convolution.
Is it?
No, this people. I mean, there.
Yes.
Cannot be.
So I think this whole complex version of representation learning, I think it's still wide open, right? It's a,
I assume you'll have an even EI term that'll have a twisted convolution.
we don't. Do we? We don't. Costas will be on the panel. That's a good question for the panel. Okay, Costas will elaborate on it. Okay, so this sort of became the state of the art. These are not, none of these are my work. So, but yeah, this is now the state of the art, and you can process images. The limitation is that obviously you need to figure out the EREPs, you code them up for your group. However, for Euclidean group, I think it's worked out, and there is a library for Euclidean group. But a lot of problems that at least I'm interested in are not in that Euclidean group.
Is there like a general reason?
You need to derive the constraints and the kernel of the convolution. That and
That's so okay.
that
But it generally applicable for
it is, but subject to having the EREPs. So that's the barrier basically. But for SO3 and Euclidean groups, it's just available.
I only see these pictures from the three. I don't see anything.
So yeah, the steerable convolution is now it's 7 years old, more 6 years old, 8 years old. So it's just a pretty natural idea as well. I think it's but again, there's a problem with finding out the EREPs and then coding them up. Now I find this work very interesting. It's pretty recent, 2023. So I think they recognize that if you want to do general group convolution, you have to derive these constraints analytically, which is very difficult, and frankly, most people don't even have the background to do it, right? And what you can do, you can recognize that at the end of the day, you just want to have an equivariant, basically, model based on those EREPs. So you could just throw it away and replace it with an equivariant MLP with respect to that group that you want. Obviously subject to the fact that you have this equivariant MLP. If such a network is available, you can just learn those bases. And then you at this point you have automated finding out those steerable kernels, and the rest is the convolution. So this was very important, I think, in automating this process. And I think we tried it on SL2 and SL3, and it's not published. Justin, my former student, he graduated. I asked him what is stopping you. He said just time. So if I go by his words, But in his thesis, he did some, early preliminary, he got some preliminary results on SL2. You can stretch and do other things on the image, and it works. However, in this particular, you have to make an extension, because in this work, they make it work for compact group. And there are details, but they have to invert a representation, and then if it's transposed, it works out. But they didn't realize that inverse and transpose is just a dual representation. So the dual representation is just another representation. You just replace it with the MLP, so it works out. But in the paper, they just talk about the orthogonal. It's not gone that far.
Before we go on, so why particularly reduce, right? So you're taking a group, you're finding representations. So you've got a matrix representation, and that's sort of sampling, and then you're using that to act on a linear vector space to affect the kernel structures. Why does that need to be irreducible? What's the?
Because we need the basis. Irreducible will be the simplest form.
You can't
Reduce it.
the matrix
Step.
size.
Right. So that's why. But otherwise, we want sort of it's irreducible. Then any other kernel will be a linear combination of those.
Yeah.
And then we make those linear combination learnable weights. So then we optimize, we will find out automatically. For example, based on these two bases, we need this one as the best filter to run through for the convolution. I guess it doesn't, it's like a basis, right? It doesn't matter.
Yeah, basis.
It doesn't matter. And I think you're right that it happens here, right?
It deals with over parameterization beautifully, right?
Which is happening here. I think once we replace it by this equivariant MLP, there's no reason this will give irreps, right? We'll just learn some basis, whatever it might be. So it's no longer irreps. Okay, so you won't be able to do much unless you have an equivariant MLP. So the MLP is basically a linear model plus nonlinear activation, ReLU. And it's obviously the reason it's powerful because you have this, universal approximation theory and all of that. So a very interesting work is EMLP. And the way they, just very shortly, what they do is that they learn a representation and then they sort of solve an iterative optimization to project it into an equivariant subspace. So they learn the feature and they project it to the equivariant subspace. And in the example they have in the paper, it's typically a Euclidean group and sort of standard groups that you see. If you try it on something like SL3, what happens is that equivariant subgroup subspace might not exist, which is a problem. So you can be aware of that limitation for more general groups, but in general, if you are working with the simpler groups and especially compact groups, I think it works fine. So this is a nice way to get that equivariant MLP. But another line of work that I would classify them as equivariant MLP, but they're different because in equivariant MLP, they're the channels, they're the features that are equivariant. In this class of work, vector neuron and linear neurons, there's a geometric channel that, just like that group convolution, is the dimension of the Lie algebra. And we just keep that dimension fixed, and then there's the channel dimension. Now the features don't need to be equivariant. Equivariance is with respect to the geometric dimension. So that puts us in two different categories. So you can get equivariance by making the channels, the features that you learn to be equivariant, or you can sort of introduce a geometric dimension that do all the actions that are with respect to that. And the idea is that vector neurons, so MLP, each activation is a node. Vector neuron made them to be a vector. It's a generalization. And in sort of linearon, it became a general vector field, left invariant vector field, basically. And so you have, for example, for SO3, you maintain this three-dimensional geometric dimension, and then you can have all sort of weights. It will act on it. It will change it to C prime instead of C. Okay, and then because these vectors rotate together, right? You can have an invariant form, invariant dot product. You can create nonlinearity. So the idea is that to replace the scalar ReLU with a vector neuron, you can use the dot. You can learn the direction K, which you see here. Now, if the input and the learned direction sort of makes less than 90-degree angle, you pass. And if not, we compute the vector rejection by removing the part that goes outside of the 90-degree. And this uses the dot product. Obviously, if they rotate together, this rotation disappears. So this became really popular because it's really simple. There's a really simple tweak to MLP, and suddenly you had in a sort of purely algebraic, and basically you have SO3 equivariant network, and it solves also the problem on point clouds. Okay, but the problem with the MLPs is obviously they don't lack the local structure of convolution, and they're not as scalable because you're working with full linear layers instead of just running small convolution on extracting features. And they can't really, these two works that I'm talking about, they can't really process images. So if you want to process images, these are not suitable for that. Now, linearons, you can think of it as a generalization of, probably this is the last thing I should talk about, generalization of vector neuron in the sense that you no longer think about vectors, but you think about coordinate string and transformation. So the input itself is a map. So when you think about the input itself as a map, then we are talking about change of basis in the using matrices, right? So I need to be equivariant with respect to basically change of basis. But why this happens is that, so if you look at the group representation, basically the problem is that find a matrix that is invertible, right? That sort of represents the group action on some vector space V. Right? That's the, well, that's not the goal of representation theory, but that's one outcome of it. The goal of the theory is to figure out all the way a group can act on vector spaces. And if you, the adjoint came up a lot. Every Lie group acts on its own Lie algebra. Lie algebra is a vector space. It's a vector space that you have all the velocities. And the adjoint by definition is this is conjugation. But it's a linear map. You can put this conjugation into a matrix called adjoint, which is a map from Lie algebra to itself. And this is the group representation in this vector space. So if my data is coming in the Lie algebra, I need to model equivariance with respect to the adjoint conjugation. That is just a straightforward consequence of this math from representation theory. So because of that, linearons is conjugation equivariant. If you specialize it to vector neuron, instead of working with R3 vectors, you need to put them in a skew matrix, 3x3 skew matrix. If you do that, then instead of left translation, left action of rotation, you have conjugation by rotation. And in this sense, now there's a new way of thinking about the network. We can think of each network to be a group or category. Each group is its own, basically, in this case, Lie algebra or Lie group.
So your neuron as a group or category is an element of an algebra.
No, the group itself is sort of covers spans, works with the whole Lie algebra. Each neuron each activation function is operating on the whole Lie algebra. In that sense, it a
The traditional NLP, a neuron is like there's a scalar number,
Scalar.
right, that gets processed and then you pass on. So what's a green dot on the right hand?
so these are not they have big ideas. But I started thinking about neurons. Maybe they are processes, because at the end of the day, a neuron is taking something and giving you something else, right? You can you can think of it maybe as a process, but it's not a typical dynamic system, because it's actually, well, it is, because if you look at if you go to jump ahead of myself, we generalize it, we use the killing form, we replace the inner product, and you get a new form. So we can think of this as a process, like this is my activation now, right? Maybe we can give it a meaning here. The signal comes in, the signal has a dimension that is in the Lie algebra, but it's also, there are other things that are not relevant to the geometry. And I compute the killing form with some weights, set a condition, whatever, they pass it. If not, this is invariant. And then I compute this term. This is still in the Lie algebra, in the geometric dimension.
Yeah. So I think the point is that the green dots are Lie algebra elements, and then you have this clever way of writing down an activation function that acts on Lie algebra.
I think you're right.
Right, and then that creates a number. Well, actually, it creates a Lie algebra element that you then push into, and then you sum that because you've got a linear vector space structure with other Lie algebra elements. That would make sense.
I think that's a better way to think about it, right? But together, if you consider all possible elements that you could get, it's the whole Lie algebra, right? Because there's no limitation on what elements of the.
Yeah, well, it's like a neuron is the whole real.
It's the whole. It spans the whole.
Right.
Yeah.
So yeah, you've got a vector, and
Yeah.
the green dots are the basis elements of the Lie algebra.
And I think of it as a process model. It maps from Lie algebra to the Lie algebra. So in that sense, it's its own little dynamic of, passing the signal. It has learnable parameters as well.
In the algebra, or it's just the weights when you evolve into the next.
Well, if the input signal is in the Lie algebra and the output is also in the Lie algebra, so it looks like the process model that we use in propagation. That's what it is.
Yeah.
So the whole network is just doing forward propagation of the dynamics of sort. There are little neurons, and the composition of them hopefully give you something more complex. So I haven't done anything with this way of looking at it, but I like it this way, because it's like a compositional dynamical system.
Just to jump around because I'm a bit lost, but then what you do is you require that when you act on the whole thing, it's a group element. You act on every neuron in the whole network with the same group element, and you want nothing to change.
If you rotate the input, then everything together.
You rotate the input, but then you rotate every algebra.
They all together rotate.
And then you rotate the output, and the whole thing should.
And I mean, there are a lot of interesting things, because the killing form is not a metric, so it works. So it's absolutely not necessary to have a metric space. And another nonlinearity that we can introduce is the bracket, because the Lie bracket is nonlinear and it is adjoint equivariant. So this is an extra nonlinearity that we get beyond activation by having the Lie algebra equation. It wasn't possible before. And then if you build that ResNet style residual layer, this, if you think of the Lie bracket as the Lie derivative, we're doing sort of the signal plus the delta that we have. Like a first order expansion of the signal. And you can do nested brackets, obviously. If you do multiple at the same time, with nested brackets. So you can build all sort of layers. I'll just show you quickly that BCH formula. I have the exponential of two Lie algebra elements. I want to figure out what's Z. This is a classic problem. There's an infinite series in the Lie algebra. It's important because we can, with Lie bracket, we can completely capture the group action. If you train this, it's very well suited for this problem with all this bracket layer Lie algebra, and you can basically get the same performance on during training and test. If you during test we rotate the input, and the performance doesn't change. But MLP usually struggles if you transform the input. The neuron is good, but it doesn't have the Lie bracket layer. And then the equation of motion for I showed this to my program manager at Air Force, and he said, "You pick the most non-rigid object." and presenting it to me as a rigid body example. I told him, "Don't worry, it was a machine learning paper." So nobody caught it. So we have the International Space Station. It's huge. It's not rigid, but whatever. Let's say it is. What we want to do, we want to learn the dynamics. You have the neural ODE is a very interesting framework. You have your, say, MLP, and you learn the vector field based on the initial condition, and then you use an off-the-shelf ODE solver to integrate it. So the neural network acts as this vector field for the dynamics. Now, if you replace that MLP with equivariant MLP, then we get equivariant neural ODE. And the previous equation is, this is, I think Rob talked about Lie-Poisson. If you write it in basically twist or angular velocity, this is the Euler equation or Euler-Poincare equation. But there's no input right now. Now, it works really good because obviously that equation is in the Lie algebra and the network is also in the Lie algebra. If you train it on multiple trajectories, you get the same performance on training and test set. If you do change a basis, you change a frame, your dynamics doesn't change. That means if you have a drone and say collect motion capture data, in theory, one is enough, right? In practice, probably maybe a couple of them. But data from different frame of reference should not affect what we learned about the dynamics in this data-driven setting. If you pick single trajectory with a lower performance, it still works. From a single trajectory, you can learn, and then with the same performance and training and test. So that's also, because it's very much like the equivariant filtering control. It's correct by construction. It has no way of going wrong. The whole network is correct by construction. I should probably stop. There's, a whole bunch of other things that I skipped. And I talked to Chankyo. We were trying to do the extension to, I think GLN is very interesting. And I think the biggest part is the reductive neurons, and I don't know what's after that right now. Anyway, so I had a robot video. Okay, one last thing I want to say is that so we extended this to GLN. Before that, it was for SLN. The biggest semi-simple group that killing form works out is SLN. But for every example, we hand code basically the basis for that Lie algebra, symplectic or SL3 or SO3. Now we can run everything on GL3 or GL4. The bases are just 1, 1, 1. It's a basically invariable matrix. And we use the same network to solve all the problems. I don't know if you would call it a lift, but I'm working with a bigger group, and I'm assuming all the subgroups will be covered. And we don't know a way to lift the data to that bigger subgroup, bigger group algebra, or we lift it to the subgroup S23, for example. But when we get results, the results are usually better or similar. So I think that touches on the idea that lifting to higher dimensional coordinates might be the way to go, and you can cover a lot of subgroups using that. So that's it from me. I'm gonna stop here. I'm gonna show you a robot skateboarding to wake you up before the panel. And you can think about, maybe ask questions that, how would you introduce symmetry in this problem? Morphological symmetry is one way, obviously, but it's a trained in simulator, zero shot, real. We only trained it on flat ground, no snow, no nothing. And it's a hybrid system. The LED shows which mode the robot is in. It's contact, gliding, and hanging the leg. So but this work didn't get nominated. It's beyond me. I don't know what else didn't get nominated for RSS. We don't have anything better. So we need vision. Okay, so the robot is fixed on the skateboard. You need vision.
This is fast, right? That's not as fast as it does it. Or is that actually at real speed?
Real speed.
Real speed, okay. Yeah.
So there's no vision. So we need vision for the robot to get on the skateboard. And I've been asking for some tricks. Maybe you jump on it and land again and
Do a kickflip.
yeah. So if you're looking for ideas, there you go. This is done. Do the next one. And yeah, I'm interested to know how you do symmetry.